At the top, I have a scale of 0 to 4,000 miles so that you understand that this scale is huge. This is your point of origin. Signals radiate either directionally or omnidirectionally. Directionally is in a straight line one direction. Omnidirectionally is equally in all distances. Equally in all directions. So this point of origin sends a signal of distress. This tower over here says we're at 090. This signal up here picks it up and it says it's 180 or straight south of where it's located. And this signal right here says it's this tower says it's 270 degrees this direction. You use what is called a polar map and you draw these lines and you get a search area. A really wonderful search area in the real world back in the day when I was doing direction finding was anywhere from 10,000 to 100,000 square miles. That was considered an amazing fix. Now that may seem like a huge area to you, and granted it is a large area, but that is considered a fantastic fix to have something this tight in this area. She didn't have that going for her. They were not direction finding on her. They were listening to her, and she was trying to pinpoint a transmitting station or getting a single line bearing and then navigating to it. And this is really important. If she could not hear that signal for whatever reason, then she couldn't get it. There were what are called ground waves, where the electrical signal, the radio wave, is skipping along the ground. There's a sky wave where it travels through the air, and that's what most people think of as radio signals. And then of course there's skip, where it goes up and it hits the ionosphere, the F2, F3 layers, and it bounces down and then comes back up and so forth. She was probably anticipating a sky wave, and I'm thinking that because of the fact that it was during the day, and the 7 megahertz signals, I don't know what frequency they were transmitting on, but the 7 megahertz signals up to about 14 megahertz work really well during the day, and those can be sky waves. So as she would have been getting closer, if she was trying to tune in on it, she would have been looking for a sky wave. As the as the sunlight begins to change, you have what's called frequency of optimum traffic, which in this case, this is just a beacon for her to hone in on. The signal may have faded, it may have gotten stronger, who knows, but if her equipment wasn't working, it was of no value to her. I want to expand on the direction finding for a moment. If you've watched the 1950s movies, you've seen two antennas. They'll be, say, 6 feet apart, 6 feet from side to side, and they're on a bar, and this bar physically rotates 360 degrees, bidirectional. These two antennas are directional. Over here you have a radio with a comparator. As the signal comes in, let's say it's 6 volts DC, and as you turn the signal, it fades to 0. When it comes back in, let's say it's 1.5 volts DC. What you have is you have the Earth. This is our transmitter right here, omnidirectional. The signal is coming all the way around the world, and it's striking these two antennas. It's coming around this way, and it's striking the two antennas. If you remember, the signal, the intensity is inversely proportional to the square of the distance, right? So your 6.5 volts here is because it's not following the curvature of the Earth coming around this way. Her directional antenna was a ring. Think of something like this. And these two pieces come down, which represent these two halves of this antenna here. This one, and they're directional. If you were looking down on the antenna, it would have a major lobe like this, and then some minor lobes. This area in between the lobes is called nulls, N-U-Ls, nulls. And these right here are minor lobes, that's the major lobe. This is what gives it direction. These antennas here are just like looking down on this circle with this major lobe. When the signal is coming straight at it, it receives the signal, it gets a 6.5 volts DC. If it's facing this direction right here, I'm going to do it in dotted lines here, and it gets the signal coming into it, it'd be the 1.5. As you compare the signal strength from this direction and that direction, you know that the antenna is physically closer this way than that way. This antenna that she had on the airplane, this circle, this spherical ring, is this antenna in a much smaller version. The really big ones are about 300 feet from one side to the other. They might even be larger than that. And they use an electrical device that compares the signals. It's a comparator. It's the same thing as this. It's just a bigger scale. And this was the direction finding state-of-the-art many, many years ago. They now rely on satellite and other devices, and this thing is a thing of the past. It's gone. They don't exist anymore. You can look them up if you want. So this is what she's dealing with. If her antenna is working, she has a signal out here, and she's using this device, and she's checking. Does she have 6.5 or does she have 1.5 volts DC coming this way? And if her signal wasn't, if her equipment was not working, she didn't have a signal to even follow. I'm going to expand slightly on direction finding for one moment, and then we'll conclude this video. Let's assume that Amelia Earhart does not have her working antenna with the two comparators going into the radio to give her her 6 volts or her 1.5 volts, right? Let's assume that isn't working. What could she have done differently? If her aircraft is set up with a rhombic antenna inside, and this is going to be somewhat difficult to show you graphically, but I'm going to try. If she has a rhombic antenna set up, and I'm going to make this just a squirrely line over here, to the radio, and this is her radio here. If she had this rhombic antenna, she could have flown in circles, like so, for some time, back and forth, and she would have been able to determine the location of this ship at Howland Island, which is transmitting the signal, right? She could have done that. This is very common in yachts even to this day, is to set up a rhombic antenna and use it for direction finding. The ship, the yacht, will go into a circle, and it will sail this circle, and what it will do is it will listen for a signal. Say it's listening to a radio station off the coast of California, for example, and it'll compare. When its heading is 131, it has a very strong to the ear signal. The rest of the time it doesn't. Every time the ship comes around and it strikes its 131 magnetic compass heading, the signal is strong, and as it goes away, the signal fades or attenuates. She could have found this ship using this method if she had an antenna that was like a rhombic. The separation on the rhombics, I think, are 1 point. It's I think 1/16 of an inch. I think that's correct. It's been a while since I've screwed with all this stuff. I think it's 1/16 of an inch. You cut your notches 1/16 of an inch on your rhombic piece of wood like this, and of course it's going to be three-dimensional, right? And you run your wires like this, just like so, into your radio, and it will give you a very good direction finding. Now the beauty of this, if a signal is coming in, whether it's AM, FM, or something else, when it's the strongest on your magnetic compass, it will give you the direction of that radio. It's working just like this because this rhombic antenna, when it's looped together, becomes directional. And I'm not going to get into the physics of that. That's beyond this scope. I'm just trying to explain what's happening. Let's pause this for 3 seconds. I know that very few people that are watching this video are military. Military maps are 50,000. Actually, it should be 50,000 to 1. The aeronautical maps are 100,000 to 1. So if you have 1 foot on the ground, the scale has significantly shrunk. If you use a 0.5 millimeter mechanical pencil like what I use, and you'll see me use this a lot in my videos, and I'll explain why in a moment. If you draw a line the thickness of that pencil lead on a 50,000 to 1 scale, that little pencil line is 1 mile in thickness on 50,000. So when you're doing, like, say, a 8-grid reference, and you punch that little dot right there, which you may or may not be able to see, but it's right there. When you punch that little dot, that thing is huge. Huge. It's monstrous. When Amelia is flying from Leahy to Howland Island, she is flying across a vast ocean, and this island, regardless of its size, is just a speck on the Earth. The diameter of the Earth is what, about 25,000 miles? And this is just a little bitty speck out in that ocean. And she has to fly and get out there to it. So for her to be off course or something is not a big deal. I'm going to cover one last topic on this, which will help you to understand what's going on as far as her flying, and then we'll continue in a next segment on a more scientific examination of what's going on. Alright, I want to explain something. Now that you understand direction finding, now that you understand crabbing, and you understand some of the issues related with her using her radio to find her direction, let's move to something else. Every one of you has seen these maps like so, and then you got these other lines over here like this, and these other lines over here like this. These are isometric measurements, and what you have is you have high pressures and low pressures. Let's say that this is a low pressure. If you have a low pressure, the air is moving in at perpendicular lines to this line of force, right? If this is a high pressure, the air is flowing out in perpendicular lines to the force. I hope that's clear. High pressure, we'll put an H here, and this is a low pressure right here, low pressure. Alright? the lines are pressing out. If this is a low pressure, the lines are pressing in as these lines are pressing against it. Got that, right? Let's erase this. As Amelia Earhart is flying from Leahy to her destination with the ship out here with, with the antenna, right? Sending the signal. She is bucking high pressure and low pressure zones. I do not know what her stuff was. The fact, this is her island here, I'll color that in. The fact that she probably ended up down here somewhere tells me that in all probability she had a high pressure zone up here with winds forcing outward like this and winds here pressing inward towards the low pressure zone, right? Because in nature everything tries to reach equilibrium. As she is flying across this way and her aircraft begins to crab, what's happening? The wind is pushing her this way, so her aircraft is going to physically turn this way. But these winds are pushing her. She's going to hold her compass direction. I'm just going to make something up. Let's say it's 089 degrees. Let's just say that that's her course, right? Because she's not flying a true east-west. She's something a little different. Let's say that she's going that. She turns her aircraft physically like this, and this wind begins to push her this way. As it's pushing her this way, if she's not watching a barometer to realize she's being pushed into a low air zone, her aircraft is going to physically be moving from here to here and eventually to here, where she's going to land on this island where they think they found her. That's just the nature of flying. Let's go back to radio direction finding for a minute. She has no signal. She doesn't fly in a circle and look for a stronger signal. She may not have even been trying to pick these up on her transmitting signal. And if somebody was transmitting to her due to skip, whether skywave, ground wave, whatever, she may not have heard them. Not knocking anything that was done. The people that planned this out were not idiots. But as she is getting swept off course, the things that could have been done, if they were done, had no effect. Tragic? Yes. Do I find fault with anybody involved? No, I don't. Because like I said, they tried to account for everything. Now, for those of you that are old enough to remember Apollo 1, Gus Grissom, Mr. White, and I believe Mr. Young, they burned in the spacecraft. If history is correct, and don't quote me on this, Mr. Borman, who was an astronaut, was asked why these astronauts died on the pad, and he is quoted, from what I remember, as saying something to the effect that they died from a failure of imagination. I'm going to write that out. It's a failure of imagination. Right? What happened is they were doing a plugs out test. That's where the spacecraft is completely disconnected and is on internal power. Nobody thought that that was a dangerous test. And as a result of that, they didn't take measures to protect against an accident. If anything killed Amelia Earhart, it was a failure of imagination. There was no backup. The fact that there's so many reports that her and Noonan didn't know how to use the radio direction finding equipment. There's so many reports that the equipment was probably damaged on takeoff and she didn't return to have it repaired. there's just this perfect storm of problems that you can do whatever you want, and because there was no abort plan, if her antenna broke, turn back. If she was unable to communicate, turn back or stop somewhere else. All these drop dead points seem to have been ignored. It's a failure of imagination. The people did not consider the fact that she wouldn't succeed because she was an accomplished pilot. Noonan, regardless of the fact that he was hard drinking and probably a functional alcoholic, was an accomplished navigator, and nobody doubted that they would succeed. Barring engine failure, they should have made it. So the next topic that we'll deal with, we'll start really digging into more on the physics of Amelia Earhart and the problems that she faced as a pilot. My conclusion is she died from a failure of imagination more than she died from a failure of equipment. The failure of equipment is technically what killed her. This is the professional cause of her death. They failed to plan, they failed to execute, and as a result, she was lost to the world. Dysfunctional vet, out.